and this is just the standard model cross section. If lambda is positive, then you can enhance the cross section. But we are still working on the, putting the, not just doing it like this way, but putting all the vertices at one loop and computing the total cross section, so at one loop order. If I have...
Do you have a comment on WW fusion?
No.
Okay, I heard that to measure the cubic coupling, it is better to use WW fusion.
At the LHC?
At the IMC.
At the LC, yeah, at LHC, I agree, but the LHC is the cross section quite small. Yeah, you can get WW and you get the Higgs, and the Higgs split into it.
ILC?
That is, yeah, for the extra node. I show only this process. I did not show the other one.
The WW fusion cross section is smaller than this problem, but I heard that WW fusion is more preferable to measure the cubic.
WW cross section could be larger than this one. It depends on which energy, because this is a T channel, and so if you go to, for example, more than 500 GeV, WW is much higher.
500 GeV, this stratum
is small.
Section is larger.
For 500, yeah, but if you go to 800 GeV, the WW is larger than this one.
No,
Yeah, so at high energy, WW is much more preferred.
Sub diagram. So that's why WW fusion is more preferred to measure the cubic.
Okay, yeah, of course, yeah, in this sense, yeah. But well, if you run at 500 GeV, this is the first one you can get. If you go to 800 GeV, then the cross section is much larger, because this T channel, it has some log dependence in the cross section. Okay, so well, if I have 5 minutes, I will just comment on this model. We just finished this paper yesterday. This is just a two singlet model, standard model, X sector extended by two singlet scalars. One singlet is inert, and the other one, the one is inert, does not have any verve, and the other one has a verve and it can mix with the standard model Higgs. So in this model we have two CP even state, H1 and H2, which are a mixture of doublet and singlet components. And by conversion we have this M1 less than M2. And we have this, as I said, because we have two singlet, one is inert. The inert is just the dark matter candidate, and it will reproduce the correct relic density. The coupling, since those two Higgs is just mixture of doublet and singlet, the coupling is just exactly like in the standard model times the cosine theta in the case of H1, or sine theta in the case of H2. The same for the gauge bosons. We did the full study, and we asked that one of them should behave like standard model Higgs, and the other one just either heavier or it's pure singlets. And we require also that the coupling, normalized to standard model coupling, should be larger than 0.9, just to reproduce the WW and ZZ signal strength cross section that are already quite measured and are consistent with the standard model. So we require this, those two quantities to be larger than 0.9. So that means when you identify your H1 to be the standard model Higgs, that means that H1 is dominated by the doublet, and the H2 is going to be pure singlet. Because the mixing, if you ask that the mixing is much higher than 0.9, that means that this Higgs field is dominated by the doublet, and the other one will be a pure singlet, or to some extent at 10% it's singlet field. We discussed the two cases. The first one is H1 is the standard model like Higgs, and the other one is heavier than 126, and it's dominated by the singlet. And the second case is H2 is the standard model like, and H1 is less than 126 GeV. And H1 could be quite large, it could be 60 or 70 GeV, but it has to be consistent with LEP data, because we know for Higgs lighter than 114 GeV, there is some data from LEP which should be satisfied. And we check LEP data, and we can have this H1 less than 126 GeV, and is still consistent with LEP data. Actually, just with this constraint here, you can avoid LHC constraint and also some of the LEP data. Those are just the direct detection cross-section, so just to show you that the model is consistent with all the xenon constraints and everything. And the most important part I want to share with you, just that in this model, so if H1 is standard model-like, that means that H2 is heavier than H1. So this H2 can decay to 2 H1 with a branch ratio which could go up to 50% or more. You can see the green line here is just the decay of H2 going to H1. That means that you can have a resonant production of a pair of standard model Higgs-like. If this branch ratio is quite large, with this mass, you can, the cross-section of a pair of H1 could be of the order, it's almost one order of magnitude bigger than the standard model cross-section. You can see it's 500 femtobarn. The standard model is of the order 30, 40 femtobarn, so it's almost one order of magnitude, more than one order of magnitude. So, and the same here for several benchmarks, so the cross-section is quite large. This is mainly due to this resonant production of the, I will show it here, so, no, sorry. Because you have the resonance production of H2 can decay to 2H1. You have the standard model part, of course you have blue going to H1 and H1 splits to 2H1, but you have another because you have 2 Higgs now, and H2 can split to 2 Higgs. In the other case, when H2 is the standard model like and H1 is less than 126, so we know that there is a constraint on the invisible decay of the Higgs. So we ask that the branch ratio of H2 going to H1 and H2 going to invisible decay should be less than 20%. And so in this, we plot the branch ratio of the Higgs going to 2H1. And so the maximum, of course, because of this constraint here, the maximum is 20% you can get here. But even with this 20%, we can get a large cross-section. If you look for pair production of H1, which can go through, you produce PP, goes to H2. This is standard model like particle. And the cross-section of this one is huge. The cross-section is 50 picobar times the branch ratio of H2, which can split to 2H1. And so if you just because this one will be modified by this sine square theta, and this is just standard model cross-section, and the branch ratio here you can get, so the cross-section is large, is 10 picobar compared to the standard model case, which is just 30 femtobarn. Here we are talking about cross-section of the order of 10 picobar. So that means that this could be an important source of production of a singlet, because this H1 here, it's a singlet, it's pure singlet. And to produce a pure singlet is in the conventional process is quite difficult. But you can get it from just from this decay of the standard model X going to 2 singlet. Since this cross-section is large, so we can reproduce this 2 singlet from this standard model process. And this, I just show you the cross-section, blue going to H2, and H2 split to 2 Higgs. Those are the red point, and you can see the maximum is slightly larger than 10 picobar. And this, the production of the standard model Higgs, followed by its decay to 2 singlet, to a pair of singlets, would be an important production of the singlet scalar. That was one of the important points. And also, you can have also this decay. H2 can decay to 3 H1 if they are lighter than, say, 40 GeV. So you can, and this branch ratio is of the order of 10 to the minus 2. So since this one is standard model-like, this also can be measured maybe with high luminosity optional DLHC. It's possible to measure this kind of branch ratio. So to conclude, I already take maybe 10 minutes. As I explained to you, so the Inert Higgs doublet model, it's we did some global analysis for this, and it seems that the model is going to be around for another 15 years, because there's still a light dark matter mass is still allowed, but also a high dark matter mass is also allowed. That means that because we know the sensitivity of the LHC to Chargino and Neutralino is of the order 300 GeV. So the sensitivity of LHC to those inert Higgs is going to be the same, means that the LHC will not see those particles if they are heavier than 300 GeV. And so the model LHC will be still there for another decade at least. I show you that Higgs to the diphoton, if with the next run of the LHC, there's still some excess in the gamma-gamma channel. That means that this lambda 3 should be negative and the charged Higgs should be less than 300 GeV. It depends how much you want to enhance this gamma-gamma. And those two processes, they are correlated. So, but R gamma-gamma is usually smaller than R gamma-Z is smaller than the diphoton mode. The LHC data, I show you that from the invisible decay constraint, you can already put some constraint on the inert Higgs doublet model. And also the triple Higgs coupling could be a good probe of physics behind standard model, because those triple coupling, they are very sensitive to this, to the details of the scalar potential. So if you have some, the scalar potential like the one I showed you, the inert Higgs doublet model, it has this freedom of taking those lambda with unitarity and perturbativity constraint. We can still have some large correction for those triple coupling, and that could give some information on the physics beyond standard model. That's it. Thank you very much.
Thank you. Okay, do you have any question? Yeah.
Okay, for the measurement of the Higgs, triple Higgs coupling, which machine between the IOC and the LHC is better, considering the background and the current design?
Well, for this one, it depends. If for the LHC, it's very difficult because the cross section is quite small. As I showed you, so the cross section, there is the best mode is the 2X. The cross section is 30 femtobarn, 30 to 50 femtobarn, depending on the uncertainty. And so, if the Higgs decay BB bar, just forget it, because the QCD background, they cannot make it. So there is some hope to measure this with one Higgs going to BB bar, the other one going to tau tau, or one Higgs going to BB bar and the other one going to gamma gamma. Because gamma gamma is very clean, so you can reconcile the things. But for the gamma gamma, you need to wait at least for 10 years after the second run of the LHC, because you need a very large luminosity. You need 3,000 inverse femtobarn. Means at the end of the, but for tau tau they need, I think, 300 inverse femtobarn. They can do it for tau tau mode, and so then they can measure the triple coupling. For the ELC, it's complicated because if you build the machine at the ELC, for what reason you want to do this machine? It's not, there is no new physics, so we know that there is no new physics at all. From the LHC, there is nothing. So then the LHC is going just to measure the Higgs mass, the top mass maybe, and the coupling of the Higgs to the top. And so it's better to start with the option 250 GeV to measure precisely the Higgs mass and the Higgs coupling to ZZ, to start with the, I showed this to start with the threshold production of the Higgs. Yeah, this one. You need to start, because it's just waste of time if you don't start here, because this is very easy. You start with this. First you measure the mass, you measure the coupling, and then you, because at linear collider you can extend easily the energy of the central mass energy. Then you go here to get the TT bar, and then you need at least this one to get the triple coupling. And the cross section is quite small because this is T channel, but as he said, so the best one maybe is WW, because for high energy, WW can split to Higgs, and the cross section is much higher than. At 500 GeV, I think this is still win, but if you go to 800 GeV, this is the best one. And then you can measure, but cross section are quite small, and you need quite a lot of luminosity to get the things done. But this, if we can have a linear muon collider, then it's very easy. At muon collider, because muon collider you get Higgs as a resonance, and then it splits, so you can measure everything.
In a tablet model, plot how much smaller size of the allowed region altogether you assume branching, invisible branching ratio to be 20%.
20%. 10 to the minus 1, 10 to minus 2, sorry. This one? The branch ratio of the order 30%, you need 10 to the minus 1, but well, it's, it's very close. This is 20%. It's this is 5. So it's about 7.
What about the likelihood?
10 to the minus 2.
The likelihood of
The other one, yeah. I would say it's quite similar. Yeah, it's here. This is 0.1. If it's the invisible is open, so you are somewhere here. So there's this region here, quite small, but there is those 2 branches here. Here you are very close to the resonance. Like I go to Higgs. So 1. So 0.5. So I think it's 2 10 to the minus 2. So I think they are consistent. So because here you are very close to the threshold region. So cross-section becomes the relic, I think, becomes quite large. This is consistent because I checked this with a lot of people. They did this portal model. It's of the same order. Because it's exactly, well, it is this lambda to chi coupling. So
Do you have any other questions?
Does your new models, do your new models change the order of phase transition, the electroweak phase transition?
Yeah, the inert, I don't think you can have the electroweak phase transition, but the second model, I explained the model with 2 singlets. The first motivation was to explain the electroweak phase transition, first order. And we did, but we need that was before 2012. And one of the Higgs should be lighter than 70 GeV, and the other one should be heavier than 300 GeV. With Higgs at 125 GeV, it's excluded. But still, it's a viable model for dark matter stuff, but not for the electroweak phase transition.
Two questions. One is there 300% enhancement of triple Higgs coupling is compatible with dark matter electricity constraint?
This we did not check now. This is just still, but it's easy to check because I did not show you this plot. This is the profile likelihood for high mass M chi the order of more than 500 GeV. So lambda chi is still, it could be quite large, of the order 1, the maximum we can get. But on those plots we did not implement the Rayleigh density constraint now. It was not there. It's just, but all the ST, unitarity constraints, perturbative constraints, all are there. All the constraint was there, but not the Rayleigh density. But as I said, so the Rayleigh density, so it will just limit this lambda chi to be in this range. But lambda chi, you know, it's a mixture of lambda 3, lambda 4, and lambda 5. You can just play with those 3 and you can tune, you can, I don't think it's complicated to realize.
Is there any implication for the vacuum stability problem in the
For what?
Vacuum stability, vacuum instability of
the potential. No, we did not study it. You need to do the to do the full RGR analysis. I don't know. Did not do it.
Is around region is somehow constrained in the likelihood technology. So
you can get if you do the running of lambda, and the other lambdas will contribute. Maybe they will affect the running of the. Because in this model, so the standard model Higgs is kind of decoupled from the other one because of the Z2 symmetry. So there is no they communicate, but only through some the Higgs. I mean, the visible and the invisible sector, they communicate through the Higgs exchange. But in the standard model, also the standard model Higgs is kind of decoupled from the other one. But if you do the full RGE analysis, group analysis for the lambda, maybe the other lambdas also will contribute when you compute the 1 and 2 loop correction. And then they may affect the stability, I mean the cutoff in which the lambda will become negative.
Any questions from younger guys? No? Okay, so we have a lot of questions. So, okay, so let us try to speak again. Thank you very much.